Yes,
Okay.
I start the recording and you can go on. Thank you.
Today's speaker is Professor Emre Alkan from Koç University. He completed his PhD in 2003 under supervision of Ken Ono, and his thesis title was Multiplicative Number Theory with Applications to Modular Forms and Enumeration of Groups. He worked at University of Illinois Urbana-Champaign from 2003 till 2006, and he has been teaching in Koç University starting in 2006 and since. His research interests include analytic number theory, classical theory of modular and automorphic forms, sieve theory, distribution statistics, Diophantine approximation, and asymptotic aspects of group theory. Let's welcome our speaker, Professor Emre Alkan.
Thank you very much for the invitation and for giving me the opportunity to speak here. So I will talk about today. So let me share my screen first. So I will be talking about prime counting functions today. So I will take a historical point of view and make many remarks along the way, okay, historical remarks. And of course, it's very difficult to discuss all the developments in a limited time, but I will be rather surfing over the results, okay, so, and then compare results with each other. So I think it will be very helpful. I mean, if you are not familiar with the subject, so you can have a pretty good idea about what the motivation is and what the progress is so far up to some point. So, of course, when I say prime counting function, the motivating question is about this function, pi of x. So it simply counts the number of prime numbers that are less than or equal to x. So, of course, we always take x to be a non-negative number here. I mean, we are not interested in negative numbers. So, and of course, the question is, it's a very old question, by the way, in the history of math. So what is the behavior of this pi of x? So this is a function that you can consider. And the first thing is, of course, as you go on, you tend to accumulate more and more prime numbers. So it's clearly a monotonically increasing function. And well, then it will have, of course, jumps. It will have jumps of height 1 exactly at the primes, okay, when you meet a prime. Of course, whenever we see a function, we tend to graph it. I mean, that's what we are trained in calculus. So I made a toy graph here, I mean, which everybody could do, but just to give us the flavor of what's going on here. So of course we start like 0 and then at 2 is prime. So we jump to 1 and you can see the jumps. And other than that, it's a step function. I mean, it's made up of steps. Okay, so, and one can continue to the right by sketching these step functions. And you can see that there are occasionally jumps of height 1 exactly at the prime coordinates here. Okay. Of course, now this is a toy graph. And well, it turns out that, well, you can think of it like this. As we go far away to the right, I mean, accumulate more and more parts of this graph, you can see that it will become more and more challenging to sketch the graph of pi of x, especially about the length of these steps. Okay, so, I mean, they might vary clearly. So, well, then, if you really try it, you will see the difficulty, I mean, to do it by hand. So I should make the first remark here. Even with the graph, it's not easy to see what happens to the graph of pi of x on a macro scale. Okay, so as you go far away to the right, I mean, it doesn't give much insight about what's going on, about the primes. So although you can accumulate more. So that's why one is interested, first of all, although, I mean, the calculus functions, for example, their behavior, we can easily discover by graphing them. I mean, that's a standard technique. But graphing this in this way doesn't give much insight into what's going on with the pi of x. Of course, now the very first result on pi of x goes to Euclid. Everybody probably knows that he's the founder of arithmetic, or all the arithmetical foundations of arithmetic we owe to Euclid. And he proved that there are infinitely many prime numbers. So, well, it's better for us to say it like that. This is just saying that pi of x tends to infinity as x tends to infinity. So we can just rewrite it like that. Okay, so this means that we will accumulate more and more. So it's monotonically increasing to infinity. So that's what we have. Now, once you, of course, see Euclid's statement, then there are, of course, many questions that come to mind. So how does pi x grow? I mean, it grows, but how does it grow? So what is the rate of growth? Okay, so can we compare this with other functions, other well-known functions? Now, Euclid's result is, of course, very old. And it's interesting that there was virtually no progress in this problem until recent times, like 1800s. And really nobody did any significant work on really strengthening Euclid's result. Now, there could be many reasons for this, well, historical reasons. I think that this problem is somehow overshadowed by other developments in math. So this was seen as an insignificant problem, probably, okay, because I mean, during the time between 1600 and 1800, of course, calculus was developing due to Newton and Leibniz. So, and of course, the important topics in math was built around differential equations and natural phenomena. So describing natural phenomenon. So that's why this was overshadowed by developments like that. Even in number theory, I mean, developments in number theory until 1800s and also later, I should say, number theory was only seen as mostly study of Diophantine equations. Okay, and you can remember the times of Fermat. And of course, the most important problem, Fermat's last theorem, is a single Diophantine equation, okay? So people were interested in such problems, even people in number theory. So it's understandable that nobody has thought about this problem. I mean, didn't spend a lot of time maybe. With one single exception before 1800, it's Euler. I mean, he didn't really state anything about pi of x. There is no indication that he was interested in the rate of growth. But Euler is responsible for proving at least that, for example, the series of reciprocals of primes is a divergent series. I mean, Euler was interested in divergent series. So that was a significant result, okay? And you can see that there's a slight strengthening of Euclid's result, okay? And so 1/2 plus 1/3 plus 1/5 and so on. That series diverges. That's what Euler showed. So of course, it immediately implies that there are infinitely many primes. So it immediately implies Euclid's result, okay? So you can see that there's a slight strengthening of Euclid's result. But of course, Euler didn't have the tools to discuss anything about rate of growth. Okay, so he didn't tackle with this problem. Now, things started to change around 1800s. So what I tell you in this lecture is what happened mainly in the last 2 centuries. Okay, and this is still an incomplete problem. Now, looking at, of course, people made tables of primes. I mean, made counts of primes up to some some x's, some values, and just by looking at those tables and counts of primes, they start to tell some insights. So they made this claim. So pi x is about x over logarithm of x. Of course, this is not precise. So I made a question mark here. What do we mean by about? Okay, so that needs a precision. Well, of course, logarithm is always the natural logarithm for us. So I indicate that. And if you have a different logarithm, I will make it clear. Now, it turns out that the very first mathematician who really discovered some results around this insight was Legendre. So a leading mathematician of his time. He wrote an influential book. And I think an edition of this book appeared in 1830s. So it's a book on theory of numbers. It's written in French, but he definitely in this book has a section on prime numbers. And then he made this statement in his book, pi x is approximately, again a question mark, what do we mean by this exactly, given by, here is the function, so x over logarithm x, but you see minus a number which is close to 1.083, and he gives more decimals. So, of course, Legendre was very well aware of the defects of this, probably. He felt that maybe this cannot be an exact measure of pi x. I mean, that's too much to expect. So he was already thinking about some errors. So he made a correction term here. And you can ask how he discovered this weird number there. So he definitely cooked up his formula, which supplies a good fit to the tables of prime counts of his time. So it's like up to 1 million probably, or maybe less. So he made a statistical analysis, and he made this to fit with the data that he had. So this was very fitting with the tables of his time, okay? So that's why he got this number. So this was a very good approximation. That's what he felt, and he checked. So that was the very first appearance of a measure of pi of x, okay, around 1830s. But now one can go with an exact formula, so one can get more ambitious. So can we write an exact statement for pi x? Legendre made an attempt also on that, and he was to some extent successful in this. So I will call this Legendre's formula. Now look at the nature of this formula. So pi of x minus pi of square root of x plus 1. And that's equal to, so this is an exact formula. So greatest integer of x minus, well, look at the sum. So p1, p2, these are all primes. So all primes up to square root of x over p1, and the greatest integer of that, and you have a plus, and then you have products of two different primes, less than or equal to square root of x, and you take the greatest integer of x over p1 times p2, and so on. Although I said dots here, there are finitely many terms here, because there are finitely many primes less than or equal to square root of x as soon as you fix x. Okay, so this stops. For example, when you have the product of all primes less than or equal to square root of x, there will be a single term in the last contributor here, which is either plus or minus. Now, if you look at it carefully, it's just using a simple counting principle. The right-hand side is just using the inclusion-exclusion principle. So Legendre really did what could be done, I mean, at his time, what was natural. So really then, the right-hand side clearly counts the number of all integers less than or equal to x, because that's their whole number, right? That are divisible by no prime less than or equal to square root of x. Because if you were trying to count this, that's what you would do by inclusion exclusion. Okay, so then that would correspond to the right-hand side. But now let's make a couple of observations. Any integer less than or equal to square root of x, of course, with the single exception of 1, 1 has a very special status. So it's divisible by a prime less than or equal to square root of x by fundamental theorem of arithmetic. I mean, that's for sure. And well, so those are gone in some sense. And any composite means not prime integer in the remaining of the interval, namely from square root of x to x. So I made this open. Well, it has to be divisible by a prime less than or equal to square root of x. Because if you take a composite number, it should be the product of two non-trivial integers. But then one of them should be less than or equal to square root of x. But then that's divisible by a prime. So there you go. So they have to be divisible by a prime less than or equal to square root of x. So then the only remaining integers that the right-hand side counts, indirectly counts, is, so it's the number of primes in this interval, square root of x to x, but that's open, together with the 1. I mean, because 1 has a special status, okay? So it's not divisible by any prime anyways. So, but then how do you count the number of primes here? So it's pi of x up to x. And that's exactly the reason why this is open. So I have to subtract pi of square root of x, okay? So some people make the definition slightly differently. They make this strictly less than, but then you might have some troubles in then representing this Legender's formula. So it's important to say less than or equal to for the definition of pi x, so you can safely do this. Okay, so this counts the primes exactly in this half open interval, but then because of the special 1, you have to add 1. So that's exactly the reason why we have to add 1. So this was Legender's exact formula. And it's kind of interesting because it could serve as an exact formula for pi of x, because after all, square root of x is a lot smaller than x. So there are fewer primes, hopefully, up to this. So with some really little error, you have a representation of pi of x. But it turns out that none of this is that useful, okay? Maybe at Legender's time, it seemed to be promising, but it's not that promising. And nevertheless, Legender did not have the tools to compare these two terms. I mean, because he didn't know anything about the size of px for any x. I mean, he had limited knowledge. I mean, he had a formula, which is a good fit, but that's an empirical formula only. So it's not clear if this holds forever, I mean, for larger and larger x's. So, but nevertheless, I think I should definitely tell you a much better way of expressing the right-hand side. You can introduce the Mobius function, and you can let P to be the product of all prime numbers less than or equal to square root of x. You can simply write the right-hand side like this: D ranging over all divisors of P. And we only care about, of course, square-free Ds, which are just products of these primes. So then mu D takes care of that, because when you have an odd number of prime numbers, prime factors, then this is -1. So it should be like that. And when you have an even number of prime factors, it should be plus. So that's exactly the definition of the Mobius function. And of course, non-square-free integers are irrelevant here. So you make it to be 0 there, since they are irrelevant. So you make the support like that, okay, only on square-free numbers. So that leads to the introduction of the Mobius function as well in a natural way. So you can simply write the right-hand side more compactly like this, where mu of d is the Mobius function. I will have more to say about Legender's findings very soon. I mean, with today's standards, I will take a look at them again. Now, this was the notation, of course, one can use. Pi of x is just a count. So we are adding ones when p is less than or equal to x. P always denotes a prime number. So now at this point, maybe I just show you an illustration. So it's always good to look at numerical tables. So I will look at, so in fact, we already have some suspicion about the macro scale of this graph. I mean, it looks like this, but how about the macro scale? So let's see what happens on the macro scale. Of course, we have computers today, so we have, I mean, prime counts up to really large numbers. So you can see the shape of the graph of pi x is the upper graph here, and the solid one. So the dotted one is the approximation somehow. Unclear how it approximates so far, but it's the graph of x over log x, okay? And it's up to 1 million. I think anybody seeing this graph should be surprised, because on the macro scale, as you can see, the graph of pi x is so smooth. I mean, you cannot even tell that it's a step function. It's made up of steps. So that's quite amusing. So on a macro scale, then really primes are behaving regularly. I mean, there's really amazing regularity, so that the graph is so smooth, okay? And this is really astonishing. I mean, I found this really surprising. And this is something that you cannot discover by hand. I mean, just see that it's up to 1 million. And that's the first thing. I mean, there is really a regularity on the macro scale, although there are irregularities, as you see on the toy graph. I mean, it just smoothens out in some sense. Okay. Now, it turns out that before Legendre, Gauss made some remarks about pi of x. Of course, Gauss made many remarks. I mean, he was a mathematician who liked to work on problems offering a lot of structure. So probably he felt that this problem on pi x didn't have much structure, but he made this remark, okay? And that was his great mark on the subject. So just by looking at prime tables of his time, as Legendre did, he made a better kind of guess. So he made this remark: a better fit for pi of x is this function, Li of x, Li of x, and it's defined like this: is the integral from 2 to x of the function 1 over logarithm of t. So he just put this as solely as an empirical observation. I mean, he didn't say anything about this. Gauss didn't say or didn't attempt to make any justifications. So he just made this remark that this is a better fit for pi of x. Now, of course, with today's standards, we can understand somehow Gauss's prediction. Now, in fact, he was a guy with extraordinary memory. So, I mean, just by looking at the prime tables, it's kind of striking that he made a very good remark. But with today's standards, we can see that this is a reasonable conjecture, really, because what do we know? Pi x over x, now from our earlier insight, pi x over x is about 1 over logarithm of x. So that's approximated kind of like that. Well, then averaging always improves statements. That's what we learn, okay? So averaging really improves the behavior statistically, and that's what we could expect. So since pi x over x is about 1 over log x, so if we average this over the whole interval from 2 to x, that's the relevant interval if you're interested in pi of x. So you expect this to be a better approximation, okay? So the average value, if you think of the calculus type average value of 1 over logarithm of t on this interval, is just this integral, but you have to divide it by x, 1 over x. Well, you can say the length is not x, but just forget about it. I mean, think of x minus 2 as x. So then this is expected to be a better fit for pi x over x, but then you can clear the x's, okay? So you can multiply both sides. So, well, then it's very reasonable, I guess, with the insight is very reasonable. So it's like an averaging. So the averaging, kind of the density really improves the approximation. That was Gauss's insight, and it turned out to be the correct insight here. So that's what he discovered. He didn't have the tools to prove such a statement, but he didn't care about it. I feel that he didn't care about it. As I have said, he was a mathematician who liked to work on problems with structure, and he didn't feel that there was motivation here. But, well, I should say something about this function. This is called the logarithmic integral. That's why Li of x. And I mean, that's for obvious reasons, since we are integrating 1 over logarithm. Of course, one wonders, can I compute this by calculus techniques? I mean, it's just an ordinary integral. So maybe I can find an antiderivative and compute this. I can write a better formula for this. And why keep the integral? Of course, Gauss had good reasons keeping this. He didn't compute it. And this really opens a new branch of math. So, for example, can you find an antiderivative for this function? It turns out that you can never do it. However hard you try with your integration methods, you can never write down an elementary antiderivative for this function. So like a finite combination of easy functions like calculus type functions. So you cannot do this in the calculus way. So you cannot offer an easy closed form evaluation of this integral. So the subject that deals with this is called differential Galwa theory. Okay, so I mean, that's a cute subject, really. It really was motivated with the introduction of such integrals into math. Okay, so, and you see, Galwa theory is really deals with solutions of polynomials, algebraic equations, but then you generalize it to differential equations, and that's the subject of differential Galwa theory. So you can ask if this function lies in like a function field generated by some elementary functions. So, and then you can make a theory. I think if one looks at this integral, one calls such things as transcendental. Okay, so it's in some ways a transcendental function. And if I ask you, can you find another example? Well, that's the e to the minus t square. That's another example, right? That's related with the normal distribution. That's again due to Gauss. E to the minus t square is another example where you cannot find an elementary antiderivative, okay? So there were really integrals like this pouring into math at those times, and that opened the way indirectly of a subject, okay? So we have to keep it as it is. I mean, we cannot calculate this. But this doesn't mean that we can't do anything. We can do some things here. For example, like a calculus student, I applied integration by parts here. Okay, anybody can apply an integration by parts. Well, you get x over log x as the boundary terms, minus 2 over log 2. And then if you calculate it, you get a plus, because this thing gives a minus again, and there's another minus here. So you get 2 to x 1 over log t squared dt. So you get a similar integral to this, but you see that the power is 1 more. So you have 1 over log t squared. Again, because of the same reasons, you cannot calculate this integral, because if you were to calculate, then you would calculate this, because these terms are easy. Okay, but since you cannot calculate this, then you cannot calculate this. But nevertheless, this gives an improvement. Why? Because these are smaller terms. Of course, this is just a constant. This is a lot bigger. And how about this integral? One can easily estimate it. 2 to x of 1 over log t squared. You can just decompose the interval at square root of x. Well, the first part up to square root of x is very small. And between square root of x and x, this is like 1 over log x squared. So then you get x over log x squared up to some constants. So that's the notation. So I can say that I can estimate it up to some constants by x over log x squared. I can find the universal constant here easily. But then that's a lot smaller than this function, right? So this is good news, because through Gauss's approximation, we can find as the first term the approximation that we had earlier, namely Legendre type approximation, okay? So we can see that as the main term, okay, main contributor there. So this means that we are on the right track, but Gauss's approximation offers a lot more. So it offers smaller terms. And of course, you don't need to stop here. I mean, you can continue this process. Okay, so you can do more, get more and more phases, I should say, of this approximation. Of course, the right question to ask, so far we don't have the right question yet. We have some empirical formulas, okay, that are posed by some mathematicians. Now, the right question to ask is first this: what happens in the long run as x goes to infinity? So I think that turns out to be the right question that will now cover all the things that we have done so far. This is what's called the asymptotic behavior of a function. Now, here is the definition. Now, a function f is asymptotic to a function g, that's the notation, if the limit as x goes to infinity in the long run of their quotient is 1. So in some sense, this is saying that they grow at the same rate. Now, you can see that this is an equivalence relation between functions. So, and it's a nice way of looking at functions. I mean, you can have a complicated function, but then if you are interested in its behavior in the long run, then you can interchange the function with an asymptotic companion, okay? So of course, a function might have lots of asymptotic companions. So you can choose maybe the best one which fits to your needs, okay? And then that's why the equivalence relation helps a lot. So you can think of the function as one of its asymptotic companions. So now this raises the question, pi x is an awkward function. So maybe now this lie of x is an asymptotic companion. So then we can look at that. Okay, that's a more natural function. Now I come to the times of now another contributor of this subject, Chebyshev. So this is around 1850s. Chebyshev was the first mathematician who really got the results about the rate of growth of pi of x. So for example, he showed that for large enough x, we have these inequalities. Pi x is, as you can see, it exceeds 0.92, and he has better approximation times x over log x, and is less than 1.105 times x over log x. So clearly pi x is growing about x over log x. So he's the first mathematician who had definitive results. So he proved this. All the earlier mathematicians had only empirical results, but on the proof side, they weren't satisfactory. But this is the first really result that confirms what we had earlier. And he made many fundamental contributions to the subject. Now, he suggested a linearization of the prime counting function. Now, the function that we offered earlier, namely this, is quite awkward. And he realized that a better function, namely theta of x, is, well, you can count the primes with weights. So he counted the primes with logarithmic weights. So if you count them as logarithm of p with this weight, then that's called the Chebyshev function theta. So that's one function he introduced. And even better, he introduced the psi of x, that's the other Chebyshev function, again with logarithmic weights, but now together with the primes, he puts also the prime powers, okay? All prime powers less than or equal to x. And you can compactly write this over all integers, and you introduce what's called the von Mangold function, that's lambda of n. So this is supported only on prime powers, and at any prime power, it takes the value of logarithm of p, regardless of whatever m is, okay? So then you can compactly write this. So this was one of the greatest contributions of Chebyshev, conceptual contribution, I should say. Now, why is this good for? Because this ties with generating functions. So really then, if you go to the Dirichlet series of lambda of n, you connect it to the Riemann zeta function, and it turns out that it's equal to minus zeta prime over zeta. So there is a very good generating function for this. in terms of the, in some sense, the logarithmic derivative of the Riemann zeta function, which I will say more in a while. Okay, so this is very suitable for a generating function because it takes, after all prime powers. So it works well with fundamental theorem of arithmetic, but the other ones are not that good. Okay, so so that was his conceptual contribution. Of course, why he was interested in such things? He was interested in settling what is known as Bertrand's postulate, that it's a conjecture of those times that there is always a prime number in this interval, x open and 2x closed, when x is greater than or equal to 1. Of course, when x is large, this is a huge interval of length x. Of course, we are expecting lots of primes here. But now the interesting part is that it universally holds for any x greater than or equal to 1. So that was Bertrand's postulate. And you can sense how one approaches this kind of a problem. So this is like equivalent to showing that pi of 2x, all primes up to 2x, minus pi of x is positive. Okay, so if you can show that, then that means that there are primes in this interval when x is greater than or equal to 1. Now, how do you show such a thing? I mean, it looks promising to show this. And now you can understand why Chebyshev's earlier inequality helps, because if you think about a lower bound for pi of 2x, so you replace this by 2x. Of course, the 2 in the denominator is not significant, but the 2 in the numerator is significant. 2 multiplies with this number, so you get something like 1.8 something, okay? But then you subtract an upper bound for pi of x, but then you subtract like 1.10 something, so well, 1.8 something exceeds that. So Chebyshev's inequalities were compatible. Immediately shows this for large x. Of course, there is some further work to specify smaller x. So you have to specify what means large x. So you have to do this more carefully, and that's what Chebyshev did. And that requires some further work. So for the remaining values, I mean limited values of x, you can check this, okay? So, and then he was able to settle Bertrand's postulate like this. Many other mathematicians, of course, gave similar results, similar proofs of Bertrand's postulate. So I should say that all of these really depend on a study of the prime factorization of the binomial coefficient. That's the central binomial coefficient 2n choose n, okay? So, and you can sense why it's related with this interval, 2n choose n. So Chebyshev really saw that a study of an arithmetic study of that binomial term, central binomial coefficient, was the key, I mean, to get to these things. So he was successful in doing this. He did a lot of other things that I cannot really reasonably go into here. He was definitely thinking of asymptotic behavior. I can tell you, he tried the asymptotic behavior of pi x divided by Li of x. So, but he wasn't successful, but he showed this result. So if you want to show a limit, of course, a good way is to look at lim sup and lim inf, namely the largest accumulation point and the smallest accumulation point. They always exist, okay? Limit may not exist, but these always exist. So, and Chebyshev really showed that lim sup of pi x over Li x is greater than or equal to 1, and lim inf of that is less than or equal to 1. So if there is a limit, then it has to be 1. This definitely shows that if there is a limit, then it has no chances, it has to be 1. So his findings strongly suggest an asymptotic relation like this. Pi x is asymptotic to, so these are the asymptotic companions of pi of x, Li of x, and of course we know that x over log x is asymptotic to Li of x because of our analysis here. I mean, that's the significant term. You can easily show. The other terms compared to this just go to 0, okay, in the asymptotic. So, I mean, this is clear. So these are now the asymptotic companions. So this puts all the earlier guesses, empirical guesses on a good foundation, okay? But he wasn't able to settle the limiting behavior. So he tried this really, but now it turns out that this sets the stage for Riemann. Now he's the next actor now. Who made the greatest contributions around 1860s. Now he has a single paper, that's the only paper he has written on the subject, on the number of primes less than a given magnitude. And of course, it's also another classical problem. I should tell you that it's the folklore problem. Find an efficient formula for the nth prime number. So now I look at this for a while. By the way, I just show you another table now, quite interesting. So we compare pi of x with its asymptotic companions, as you can see, these two companions. So this is an extensive table up to 10 to the 22, as you can see. I mean, at Gauss's time, we didn't have this information. Now, if you compare, you always see that Li of x is a lot better in terms of approximating pi of x. I mean, one sees that Li of x is a lot better than x over log x. And one can even make some conjectures just by looking at those. So it's really an interesting comparison between the two. For example, if you look at the values of x over log x, they are always, with the exception of the first one, they're always smaller than pi of x. I mean, they always look smaller. And Li of x looks always larger than the values of pi of x's. I mean, just look all these values. Li of x exceeds pi of x, but this is smaller than pi of x, which was also in agreement with the graph. I mean, x over log x in the long run was always below pi of x. So things are in agreement. So I think it's useful to look at just comparisons like this. And you can see that even at small bounds like this, the difference is quite small, okay, between pi x and Li of x. So it's a pretty good approximation. Okay, so this is really amusing. So I find this amusing, really. A transcendental function approximating a function that has a purely arithmetic definition. Okay. Now, of course, Riemann, although he didn't say it in this paper, he knew about Chibyshev's work. Now, how could he know? He didn't have any correspondence with Chibyshev, but Riemann had great correspondence with Dirichlet. Okay, and Dirichlet had known Chibyshev's work. Probably he told Riemann about Chibyshev's findings. Okay, and then one can prove it really on a page from Riemann's writings. So that this is some scrap sheet that some of the calculations of Riemann that you can see here. And at one point here, he really writes Herrn Chibyshev. Okay, so you can see it here. He was trying to write kind of a dedication to Chibyshev, probably. He was practicing now there, and you can definitely see that he was aware of Chibyshev. So this is like a proof of it, really, together with some other things, computations. So I just took a translation. So you can find the translation of his paper. And it's kind of interesting because this is his only paper, and his wording I find interesting here. First of all, Riemann was given a task from the academy. He was given an honor, and really the academy gave him a task. I mean, it's understood like this. He has the privilege of communicating an investigation on the frequency of prime numbers. And he says that this is a subject because of the interest shown in it by Gauss and Dirichlet. Of course, he mentions them. So like trying to say that it's an important subject, and that's why I do work on it. But now his wording here is interesting. Over many years, seems not wholly unworthy of such a communication. He just doesn't say that it's worthy of communication. So he just makes it negative like this, not wholly unworthy. Okay, so it's interesting why he chooses this. why he chose this phrase there. So, I mean, he was trying to give the impression that it's not a central problem, okay? But nevertheless, he was interested in it. And now he says, if you want a formula, then I give it to you. So he was like toying with the prime counting function. And he really succeeds to some extent here. He starts with the Riemann Zeta function. And of course, Euler's product for it, I mean, which was known to Euler, but his main conceptual contribution was considering complex values of S. Euler was only interested in real values, but now that was Riemann's main conceptual contribution. And he makes a study of this. And he first tries to find a formula which is valid on the whole complex plane, except the singularity at one. And he carries out this task. And it's a very short paper because many of the details are missed. And of course, you always talk about the Riemann hypothesis at some point. It's just a single sentence here. I mean, he doesn't even mention it clearly, but that's what later mathematicians understood, that that's really an important part of this. I mean, the main task of Riemann was getting a formula, okay? In fact, an exact formula for pi of x. And he succeeded to some extent in this. He got a formula for pi of x, an exact analytical formula, which contains the function li of x together with the zeros of the Riemann zeta function, the complex zeros, okay? So this is a complicated formula, which I will not produce here. But rather than doing that, first I get back to the formula for the primes. So another problem, a closely related problem, here is the sequence of primes. So I wrote them in a different way, is how you write a sequence. So P1 is 2, P2 is 3, P3 is 5, so on. And the nth prime in the list is Pn. So of course, we see such problems in our childhood. I mean, they give us a sequence like this and they ask, what is the next term? So you have to guess it somehow. You have to discover the pattern, you guess it, okay? So it's just fun to write primes like this. Of course, if you had an efficient formula for prime numbers, then you could just plug in and then you would get the Pn. For example, you could find P 10 to the 6, the millionth prime, just by plugging in 10 to the 6 into a formula and compute, if that was possible. Now, I should say that this problem is almost interchangeable with the problem of finding an efficient formula for pi of x. So I will give you the flavor of that. And this is exactly what Riemann was considering in this paper, an exact formula for pi of x, because you can do the following trick. So pi at Pn, what is pi at Pn? Definitely, by its definition, there are m primes up to this point, so it's obviously n. But if you have a good formula, so that's what we expect. Pi of Pn is, well, we expect it to be li of Pn. Now, but we cannot expect it to be perfect. So we have to allow some error there, okay? And that's why I called plus En, either a positive or negative. We don't know, okay, of the sign of the error. But we expect En to be a relatively small error we would like to control. Then, well, then if you have this formula somehow at your disposal, which I use a toy formula only, not Riemann's, but then you can invert this. So you can apply the inverse of logarithmic integral to both sides and you can solve for Pn. Then Pn would be the inverse function of logarithmic integral at n minus En. Then you can subtract the error. So here is a formula for Pn, okay? Of course, Li is invertible because it's monotonically strictly increasing function because of its definition. So we can invert it, okay? So we can get at least an approximate formula for Pn. So the two problems are closely related, as you can see, through this toy consideration, I should say. I mean, this is not a very serious consideration because it suffers from the defect that we don't know anything about En, Okay, how do we control this? But nevertheless, it promises a little bit, okay, and says that the two problems are really relevant to each other. Of course, as we have seen on the first page of his paper, this requires a study of the Riemann zeta function. When, of course, this is the half plane, when real part of the complex variable S is bigger than 1, where this series converges, and then by analytic continuation, it has continuations. So, and that's what Riemann did. So, in particular, he uses a transform of logarithm of zeta of S. Remember that we had the product representation, and the product representation goes very well with a logarithm. And then somehow he gets a representation of this, and then he uses like an integral transform idea, and then he inverts the transform. So what he's doing at his time is not completely justified, but like 50 years later, these steps were done in a different way. But nevertheless, he was successful in obtaining an expansion for pi of x. This is stated briefly in his paper, and which depends on the roots, on the zeros of the Riemann zeta function. I will not state that formula as it depends on analytic continuations of the logarithmic integral as well. So it's awkward to state, but that's why I just state Riemann's approximation. Riemann felt that the main terms in his approximation looked like this. Okay, so he said that this is a better approximation to pi of x. So as you can see, Li of x, but L is in capital letters. So I will mention what this means. Plus, well, it's just a sum of some oscillating terms. Mobius function, Li evaluated at x to the 1 over n's. So much smaller values than x, right? So like square root, cube root, and things like that. So these are smaller terms. So nevertheless, there is an oscillating contribution here of smaller terms. There are more terms in Riemann's exact formula, but he neglects them somehow because they look awkward, and they are like periodic terms which depend on complex exponentiation. So that's why Riemann avoided them in his empirical approximation. So he states that this is empirically a much better approximation to pi of x. Now, of course, along the way, Riemann needed a more intrinsic definition of the logarithmic integral. After all, the lower limit of the logarithmic integral looks a little bit arbitrary. We put 2 there at the beginning, but it turns out to be better if we do it at 0. So that's the definition, intrinsic definition that Riemann offers. But I mean, he uses this, but there are some problems here because of the singularity at 1, okay? And you can only do it in a symmetric way. So as it stands, it's a divergent integral. But if you take the limit around 1 in a symmetric way, well, since logarithm changes sign, they cancel each other and you get a convergent thing. And this is exactly the intrinsic definition of the logarithmic integral that Riemann uses, and it is suitable for his arguments, for the analytic continuations, not our earlier definition. But it's harmless for us because Lix differs from capital Lix only up to a constant. Okay, it turns out that this is not a very serious restriction, only important for Riemann's argument. Okay. Now, as you can see, this looks like a series, but indeed there are finitely many terms again here, because the series on n terminates as soon as this number is less than 2. So the terms are insignificant then, so they become 0. So, and you can see that, I mean, there are logarithmically many terms in the sum. So this number of the terms here is not large. It's just logarithmic. So really you can test Riemann's formula, empirical formula. By the way, he is not able to prove that pi x is somehow equal to this, or he cannot tell anything about the error. He cannot control the error. So he says in the paper that he's well aware of the defects of this approximation, that he cannot control the error, but he poses for later mathematicians to think about this, okay? To think about this oscillation. So as you can see, the first term here is like Gauss's approximation, okay? But he has more terms. Of course, I wrote a few terms for Riemann's formula. So I said approximate. So we are not sure about this, but pi x, we expect it to be very close to. So of course, the main term is Li of x, capital Li. Now the first term here is, now Mobius function, of course, takes minus values at 2, 3, and 5. So we have some negative contributions. And then it becomes positive at 6, because 6 is the product of 2 primes. And then minus, and it continues like this. Now you can easily work on this right-hand side. You see that Li of x is asymptotic to x over log x. We knew this. So you can really, from Riemann's empirical formula, you can suggest a kind of a formula like this. Pi x is maybe equal to, elaborating on Riemann's approximation, Li of x, main term. So let's just write the secondary term here, minus 1 over 2 Li square root of x. But now all the other terms, so for example, this x to the 1 over 5. So this is less than x to the 1 over 5, definitely. All the other terms are less than x to the 1 over 5. There are logarithmically many. So that's good. So all of them are smaller than x to the 1 over 3. This itself is smaller than x to the 1 over 3. So when you take the absolute value of all these terms, you can fit them into one error like this, which I just write a big O. So the error is about x to the cube root. So it's a lot smaller than the secondary term. So it's amusing that Riemann's now empirical approximation could lead to a formula like this with an error, okay? So one can try to prove this or work towards a proof of this thing, okay? So it offers now a very interesting secondary term, which Gauss didn't have, okay? And well, incidentally, of course, if you believe this, this also gives another thing, that now look at this. Now this term is, of course, positive or negative. It's a lot smaller than this, okay, the size of this, but this is negative. This gives a negative contribution in the long run, because Li, of course, is a positive function. Okay, so then this incidentally tells you that pi of x is always less than Li of x, okay, because of this in the long run. And this is a prediction, it turns out, that made by Gauss a lot earlier, okay? So in fact, it fits with our table as well, because of our table, we were also seeing that prediction as well. I mean, all these values were less than Li of x. I mean, up to 10 to the 22. I mean, so it's just very promising. And Riemann's empirical formula also suggests that, okay, incidentally, but it offers more. Now, I made a comparison. There is a table of comparison with Riemann's formula, namely, this empirical approximation, and Gauss's formula, only Li of x. So, and it's the next table. So up to 10 million, you can see the errors in Riemann's approximation, and you can see the errors in Gauss's approximation. So these are the errors with Li of x, but these are now with the terms that Riemann gave, more terms. So it's astonishingly better, much better. And of course, Gauss's errors are always look positive, but Riemann's errors, as you can see, could be negative as well. So it's quite amusing that at 10 million, the error is only 88. So, I mean, it captures the number of primes in a very accurate way. So because of our earlier connections, then he has a good formula for Pn. I mean, he can locate large primes very well with this formula in some sense. By the way, there are some formulas for the nth prime, I mean, there are exact formulas. They all depend on Wilson's congruence, because Wilson's congruence gives a characterization of primes. So using that, you can give a formula for Pn involving factorials, but it turns out that that's not practical. So it takes huge amount of time to implement those formulas. So no one has yet found a practical formula for Pn. So that's still an open problem, although there are some formulas. Now, here comes now the asymptotic behavior finally. Hadamard and Vallée-Poisson is 1896, like 100 years later than Gauss. So the Longsword prime number theorem, so that these are the asymptotic companions of pi of x. So they were able to settle this. Now, so the asymptotic behavior was understood. But you see, this is not good enough also for another reason. I mean, you have to say more, because this asymptotic behavior does not tell much about the error in the approximation. Although they are quotient in the limit tends to 1, how about the error? So from the asymptotic behavior, you can deduce only what is the error in the approximation. It's pi x minus li x, and you want to take its absolute value. And this prime number theorem just tells you that this is little of Li of x. So this error is only insignificant only with respect to the main term, Li of x. So this means if you divide this by Li of x, you have a function here that tends to 0 as x tends to infinity. So this is not very promising for, of course, for people who want to see something about the approximation, who want to see something about the error. Okay, so the asymptotic was, of course, the very first step, but it still can't control the error very well. Okay, so with a statement like this, of course, we cannot say much about the validity of such things. Okay, and it's still not good enough. Of course, now with that, we go to the next step. Now, Vallée-Poisson, of course, continued further together with Landau. I mean, they independently, just a couple of years after the prime number theorem was obtained, they got an error term. So this is now sufficient for many needs. So PNT with classical error term, that's what we can call it. So pi x is, now this is good. Now this is answering our needs, is equal to li of x, the main term, plus, well, an error term under control. So the error term is a constant multiple of x times e to the minus c times square root of logarithm of x. So there is some constant like this, c positive as x goes to infinity. So this means that you have some control on pi x minus li x. Okay, so this gives the control. Now, is this a good control? Now I start to now give some insights here for you. So what kind of a function is this? E to the c times square root of log x. So you can easily see that it grows faster than any power of logarithm of x. Okay, so for any k positive, I mean, you can easily see, just take the log of both sides. So this is like log, but this is like square root of log. Okay, so this is a lot faster. So, and I'm dividing by that here because of that minus sign. So now this really closes the phases in some sense, because what we knew earlier from li of x, it was very good with partial integrations. So we can continue with partial integrations. Now this term is much better than any power of log. For example, now we can take a next step and we can improve our formula on pi of x. Now, just by integrating by parts, li of x, we can get this formula. Pi of x is x over log x plus a secondary term, x over log x squared. Now you get, of course, an integral from 2 to x of 1 over log t cubed, because we did integration by parts. But that term is about x over log x cubed, that integral. But this is a lot smaller than that because this beats any logarithmic power. So you can bury that into that. So you see the PNT with classical error term really allows us to get secondary terms or as many terms as we want in this approximation. So we get, for example, an asymptotic formula, if you like, a much better formula as x goes to infinity. So you see now we see something that we didn't know before. X over log x is not a very good approximation of pi of x, because if you just subtract, then the error is as significant as x over log x squared, because this is a lot smaller than that. So there is a lot of error that you make. I mean, this is still a large number compared to x. So then this means that the very first approximations that offered based on empirical data is not that good. I mean, it's not that promising because the error is very large, as you can see. But Li of x is much better. That's a much better approximation to pi of x because this is a lot smaller than this error, for example, that we make here. So that's why getting PNTs with better and better error terms, but keeping the Li of x is a must. I mean, if you want to make improvements. So the very first approximation was not that good. In fact, let me now revisit Legender's toy approximation that I discussed at the beginning. So under the light of this formula now, okay, which we got easily from, of course, the prime number theorem with classical error term. Of course, you can say that pi of x, you can define a function like this, a correction term. Imagine that pi of x is equal to x over log x minus a correction function. Stands for an error, okay? Well, you can always define this function. Just solve for ax. Ax is simply this function. Log x is minus x over pi x. That's the definition of ax. And it's well defined, of course, when x is greater than or equal to 2, so that this is not 0. Pi of x is not 0, so you can define this. Okay, now, so let's just try to say something about this a of x. First of all, because of our definition of a of x, it's equal to pi of x, but pi of x is equal to this, so then these two things are equal. So then you can say x over log x minus ax is equal to this. X over log x plus x over log x squared plus the error, which is at the order x over log x cubed. Of course, you can solve for ax easily here, okay, keeping the all terms. I mean, anybody can solve for ax. I will not bore you, of course, with the algebra here. If you solve for ax, you get this, okay? So if you do the algebra, ax becomes like this, 1 plus O of 1 over log x divided by 1 plus 1 over log x, and then error term, O of 1 over log x squared. But now it's clear that in the long run, as x goes to infinity, just let x go to infinity, the error terms definitely drop to 0. This drops to 0, so you get 1. So limit as x goes to infinity of a of x, namely the correction term, correction function should tend to 1. I mean, it has no other chances. But what allowed us to get this conclusion is the secondary term here, okay? And that was possible because of this new form of prime number theorem. I mean, if you don't have the secondary term, you can't get it only with the first term. So there are interesting things going on. So we have an improvement. So you see, if Legendre, we can definitely see that Legendre's approximation is not the best in the long run, okay? Because in the long run, the correction term should approach to 1. I mean, that's what we see from the theory now. And in fact, among all asymptotic companions of pi x of this form, of course, asymptotically, any a is good here. Okay, so you can put any constant a. Asymptotically, they are in the same equivalence class. But now we can distinguish between the asymptotic companions. Now we can see that through this analysis, a is equal to 1 is the best case. Any other choice other than 1 is no good, okay, because it doesn't fit with this. Okay, so this
Sorry,
means,
Professor Alkan.
yes,
There's a question.
yes.
Amir Jafari has asked that Approach to zero. He has asked approach to zero.
It approaches to 1.
Approach to 1.
Yeah, because these terms are approaching to 0 as x goes
Okay.
to infinity. So this approaches to 1. Okay.
Okay.
So
Thanks. Sorry about that.
So if you were to put a constant here, in the long run, you have no choices. You have to put 1. And this means that Legender's toy formula could not be the best one. I mean, it was okay with tables of his time, but in the long run, it's not good. Okay. So I think this is a very pretty outcome of the improvements of having more and more terms, which was possible through this analysis. Now I will give you another outcome. So let us compare the number of primes in this interval, 0 to x, or you could say 2 to x. I mean, not important to put 0 here, but now compare it with the huge interval. I mean, that was the content of Chebyshev's work, x to 2x. I mean, there are also lots of primes definitely in this interval because their length is exactly the same. Okay, so I made a little picture here. I mean, both are huge intervals. So, well, that was a question, I mean, that people considered. Can I compare the number of primes in these intervals and say something definite about them? So, well, this is like saying compare pi of x with pi 2x minus pi of x, because you want to subtract here to get the primes in this part. Okay, as you can see, we cannot distinguish between them very well with only the asymptotics that's given by the prime number theorem, because you can definitely write pi of x is asymptotic to x over log x. Now that's another way of writing the asymptotic formulas. You can say 1 plus little o of 1. So that's a constant or a function, you can say, going to 0 as x goes to infinity. So you bury this in this little o notation, and you can write equalities like this. So you can represent asymptotics through this formula. So you can say that that's prime number theorem. I mean, without the error term. And you can make a similar game with this, pi 2x minus pi of x. For pi 2x, you can put the asymptotic formula, 1 plus little o of 1, 2x over log of 2x. And then you subtract pi of x. So you put this formula there, 1 plus O1 x over log x. Now it turns out that this 2 in the denominator is insignificant. I mean, log changes very little by products like that, okay? Because it turns this into a sum of log 2 and log x, so that has very little effect. And one can justify, which I will not, so but 2 is significant in the numerator. So this 2 is multiplied here, so we can safely say that the first term is 2 plus little o of 1 times x over log x, and you just subtract minus 1 plus little o of 1 x over log x. But then you can do this subtraction here. You definitely get 1 plus O1 x over log x. So you see that both of these functions, pi of x and pi of 2x minus pi of x, through this easy asymptotics consideration, depending on prime number theorem, they are asymptotic companions. So they are asymptotic to each other. I mean, that's very easy to see, which I will not say more. So pi 2x minus pi of x is asymptotic to pi of x. That's easy to see. But that doesn't serve for us. Of course, this means that there are lots of primes also here, like about the primes that are here. But are there more primes here? Are there fewer primes here? This doesn't answer that question because it doesn't tell you anything about significant about the error, rather than saying little o. Okay, so it doesn't say that. You see, let's go to a better analysis now. Let's feed in our improved form. So I will use this now. This secondary term will help. Okay, so I will now try to feed this into this and try to proceed. Okay, so I will write pi 2x. So I just plug in 2x everywhere in the above formula. I simply do that. 2x over log 2x plus 2x over log 2x squared. Of course, the O term, I don't need to write the 2's because I can bury them into the O. Okay, I can write a different constant and I can just write this. And of course, that's the formula for pi of x. I replicate that. I simply subtract now in the following way. I look at pi 2x minus 2 times pi of x. So I combine them now. So now I do this suggestive calculation, pi 2x minus 2 times pi x. So I multiply everything here by 2 and subtract. Of course, this is not affected by multiplying by 2. I can combine the all terms, they are the same. But I can just subtract 2x over log 2x minus 2x over log x from this. Now I have secondary terms, 2x over log 2x squared minus 2x over log x squared. So I have this. Now let's work it out. Let's look at this pair, 2x over log 2x. So now I will be more careful. So as I have said, log 2x is log x plus log 2. I factor the heaviest part here, 2x over log x. Then I have 1 plus log 2 over log x. Then I see the main term, 2x over log x. But then I have 1 over 1 plus something very little. Okay, if x is large, this is very little. And you can use the geometric series formula. So this is like 1 minus, since I have a plus, it becomes a minus here. 1 minus log 2 over log x plus higher terms, which are small because they are like O of 1 over log x squared. So I can definitely write this for this. And then I can multiply. So it just is easily seen to be this. 2x over log x minus 2 log 2, you can see the secondary term, 2 log 2 x over log x squared plus O. Of course, O term becomes, 2 is not important, but you have an x and you have log x cubed because there is another log. So the O term becomes like this, O of x over log x cubed. Now we have another pair here, but you get the idea. We can similarly work them out like this. So that's the first thing I get out of this. So you see, I have a study of this, but when I subtract 2x over log x, I cancel this term. So now the first pair here, 2x over log 2x minus 2x over log x, I have an exact formula for that with an O term. So it's minus 2 log 2 x over log x squared plus O of x over log x cubed. I carry out a similar discussion with the second pair. So I look at that and similar discussions, which I avoid. So I don't want to bore you now with more similar calculations. You easily see that it's like this. But when you subtract this, you easily see that you get this, which can be buried into the error term. Now, easily combining these calculations, one gets that pi 2x minus 2 times pi of x. What happens now? You see, we have this main term still surviving, and all the other terms are O terms, and they are O of x over log x cubed terms. That's the error term. But now we got something interesting because now we have a negative main term. This is a negative contribution because 2 log 2 is a positive number. The rest is positive. This is a negative contribution. Of course, this negativity is a lot bigger than the error term. I mean, x over log x cubed is a lot smaller than this. Okay, now we have verified in an interesting way, as you can see, the following, that limit as x goes to infinity of this thing is definitely negative infinity because this is the heaviest term, which is negative. But now this is pi 2x minus pi of x minus pi of x. I can just write it like this, and I see that it's going to minus infinity now. I have verified it. So now this means that this is the number of primes in the interval from x to 2x. Well, when I subtract the number of primes up to x, then I go to minus infinity. So this means that there are really fewer primes in this interval, in the interval x to 2x, and really in this sense, I mean, there are fewer, and we have a measure of it. I think it's kind of interesting, okay, so that we can do such things. So the ordinary asymptotics can't do that. It's not precise enough to make that distinction. but we can now compare even such things, okay? That in some sense, there are fewer primes, much fewer than primes here. And that's in agreement with the vague behavior that in some sense primes thin out, okay, as you go far away, okay, in some sense. So after you exceed the half midpoint of an interval, so they thin out in some sense. Okay, and this is a measure of that. Okay, so now, as you see, we are getting things that we didn't dream maybe at the beginning. So I find these very interesting outcomes of the theory. I mean, this is not just for the intrinsic interest, but we are getting concrete results. What I did here was first remarked by Landau, okay, so who was a major player, of course, in the prime number theorems. And now another surprise came in 1915 with Littlewood. Now this is even more astonishing. So he showed that pi x minus Lie of x, okay, we were interested in this because we needed to know what the error was doing, okay. He proved that this changes sign infinitely often. So this is a sign changing function. So now this destroys all the earlier formulas, all the predictions. For example, it destroys this formula of that we elaborated on Riemann. So this formula can't be true in the long run because it suggests that pi x is less than Lie x in the long run, but it contradicts Littlewood's statement. So Littlewood really initiated the oscillation behavior of error terms, okay? This is another study in the subject, okay? So oscillation of error terms. So the earlier formula that we offered cannot be true in the long run. Now we disproved it because of Littlewood's formula, okay? I think it was a surprise. So the early prediction of Gauss is also disproved with Littlewood's theorem. So now the subject is full of surprises. You cannot only depend on numerical data. I mean, it was up to 10 to the 22, pi x was less than Lie of x. But then this is not always true. So this is kind of amusing. So, and there is really much to be done in the subject, I should say. Now, I should go back to Legender's formula as well. Now, let me go to the look at Legender's formula with a more critical eye. So pi x minus pi of square root of x plus 1. Of course, we need to write the right-hand side, the inclusion, exclusion like this. Now one is tempted, I mean, to write this like this. Greatest integer can be written like this, the number itself minus the fractional part, which is always a number less than 1 but greater than or equal to 0, right? So you can write this term like x over d minus the fractional part of x over d. So you can work on the right-hand side. After all, it's an exact formula for this. So let's try to elaborate on this. Then you can decompose this into two sums. Now the first sum, of course, can be written as a product. It's easily seen. So you can take the x out, but the rest you can write as a product of 1 minus 1 over p's, and p were less than or equal to square root of x. Remember, that was the definition of capital P. We were considering all primes. So there you go. We have this term minus, of course, this thing. D dividing P, a sum over all divisors of P, mu D, fractional part of x over D. Now, everyone looking at this would kind of see that this is like the main contribution because it's x times something here. Okay, and maybe this is an error because mu is a small function. It takes values minus 1, 1, and 0. Okay, fractional part is a small function. It's bounded always by 1 in absolute value, so or just itself. So the error may be carelessly we can just estimate. So let's estimate the error. Just we think of this as error. Of course, then you can replace these by 1, and then it's just all the number of divisors of P. Okay, but then what is that? What is the number of divisors of P? It's like finding all the subsets of a set with this many elements. So this is the number of distinct prime divisors of P, omega of capital P. So all subsets is like 2 to the omega P. So that's definitely bounded by that. But what was this? How many primes, how many distinct primes are dividing P? Those are exactly all the primes that are less than or equal to square root of x. So this is nothing but 2 to the pi of square root of x. Okay, we can say that that's a control of the error term. But are we good with this? Now let's look at this with a critical eye. 2 to the pi over square root of x. Let's remember Chebyshev's lower bound. It says that this is greater than or equal to 2 to the pi square root of x is really bigger than a constant times square root of x over log square root of x. But this is huge. I mean, if you think about this, this is much bigger than x. Okay, I mean, anybody can see that this is much bigger than x. So this can't be error because it's just much bigger than what we call the main term, because the main term is definitely less than x. I mean, there are some factors here less than 1. So this is useless. I mean, this way of looking at it is useless. But then still we have the question, what is the magnitude of the error? What is the true magnitude here of this thing? Okay, what do we have in reality here? What's going on with Legendre's formula? Now let's look at it now with the prime number theorem. First of all, we know the behavior of the left-hand side. Of course, pi of x minus pi square root of x plus 1. This is a lot smaller, definitely. I mean, PNT now guarantees that. That's asymptotic to x over log x. So 1 plus little o of 1 over x over log x. Now, I should recall at this point another historical result due to Mertens from 1870s. Mertens studied the asymptotic behavior of such products over primes. And that becomes handy here. So with his formula now, we can say that this product that we need here, so we just plug in square root of x into Mertens' formula. So this is Mertens' formula, e to the minus gamma plus little o of 1 over log square root of x. Of course, you can write it as, because of the square root here, 2 times e to the minus gamma plus little o of 1 over log of x. So this thing is like a constant, asymptotic to a constant over log of x, which is what we expect. I mean, because this is like x divided by log of x. But what is this gamma doing here? I mean, in fact, that's the whole content of Mertens' formula. He made this very precise. He found this constant precisely. That's the tough part in this, okay? That requires really a delicate analysis. That it's not trivial to do, I can tell you. It is not even done in introductory courses on analytic number theory. It's left out. But if you really do it in the Mertens way, then this number, of course, this gamma is what's called the Euler-Masteronic constant. Okay, it's a famous constant. Gamma is like this. It's something that you are familiar with. Harmonic series minus log n, and you take the limit. So, and here is an approximation. It's like 0.5772, something like that. But then we can compute this number, okay, because that will give us the behavior of what we call the main term here. We know the behavior of this, so we can subtract and we can find the error, okay, we can solve. So now it turns out that if you take your pocket calculator and just calculate this number, 2 times e to the minus gamma, you get something like this, a little bit bigger than 1. That's the whole point. I mean, it's bigger than 1. So if you solve for this term, mu d fractional part of x over d, well, you get this definitely, 2 times e to the minus gamma minus 1 plus something going to 0 times that whole thing is multiplied by x over log x. Now, of course, the important thing here is that that's a positive number. Okay, so that's positive. So there is a contribution here. So this means that the error term is genuinely big. Okay, it's really big. I mean, however hard we try to estimate it like this, it will not be sufficient. Okay, we cannot make it small like this. Okay, with considerations like this, because in reality, it's really big. It's as big as, in some sense, the same order as the main term. Okay. So, and in fact, it was nice to discover this. So the error term is genuinely big. And this opens the gate for what one calls sieve theory. Okay, so Legendre's formula is the first appearance of sieve formulas. And there are lots of elaborations on this, okay, and which, of course, I cannot reasonably go into in limited time, but it's, I think it's very beneficial to see this. As you can see, I'm just surfing over results. I mean, I cannot just show you proofs of any results, but if you surf over results, then you see the connections. It's very good to have a recipe like this so that you can learn some of these results in detail with more motivation, okay, and you can see why they are useful. Now, what are we doing nowadays? So I just chose a result from 1976. Now, the Riemann hypothesis, the famous statement that all the critical zeros of the Riemann zeta function have a real part equal to 1/2, that's simply a statement about the error in the approximation of pi x from Lie of x. Okay, so Riemann hypothesis is equivalent to this statement. You see how precise it is. So the error is less than 1/8 pi square root of x log of x. So this is a little bit bigger than square root of x. So even the Riemann hypothesis cannot give you a smaller control on the error. So there is still a deficiency, as you can see. And this statement holding for all x greater than or equal to, well, a weird number, 2,657. So there is a lot of numerical study behind this. It's tough to prove this, and that's the result of Schoenfeld. Very numerical, but nevertheless, it's an important result. So it's equivalent to the millennium problem RH, okay? Now, how do we stand on the best result on the error term? We have the classical error term of Landau and Poisson. Now, the best error term looks like this so far as I know. So pi x is Lie of x plus an error term like that. Now, you can see that it's still an exponential, but with a better exponent. So instead of 1/2, it's 3/5, a little bit bigger. So this is the Vinogradov-Korobov estimate on the error from the 60s. And it still seems to be the best. It hasn't been improved. So you can see why the subject is difficult. So, well, at the beginning of my talk, I said prime counting functions. Why I said functions, I mean, I was only trying to count pi of x, but you can apply the same idea to subsets of primes with structure. For example, you can consider primes in arithmetic progressions, and Dirichlet was the first mathematician to show that there are infinitely many primes on admissible arithmetic progressions. So of course, strengthening of this result is this. The number of primes which are congruent to A modulo Q, A and Q are relatively prime, that are less than or equal to X, are given like this. Of course, you expect Lie of X, but divided by the congruence classes, the number of congruence classes, which is phi of Q, that's Euler's function. So they are equally distributed among the phi Q congruence classes, primes. And there is this, again, classical error term here. So that's a result that we have on primes in arithmetic progressions. Now, of course, if you dive deeper into this, there is a bug really comes into the game, which is called the Seagull Zero, okay? That's a real zero that we cannot avoid when you study the theory of L functions. Okay, and that's the most frustrating part of modern number theory, to eliminate the existence of Seagull Zero. And it complicates the study of primes in arithmetic progressions in an essential way. So if you study more on this, you face, I mean, somebody, of course, thinking about settling the Riemann hypothesis or the general forms of Riemann hypothesis, sooner or later should face elimination of the Seagull zeros. Okay, so it's just a must in the subject, but it's still an open problem to eliminate the Seagull zeros. Okay, which is kind of, they're elusive in some sense. Now, I thought I should maybe conclude with some evidence supporting the Riemann hypothesis. Now, why do we believe it's true? Why do we believe such an error term? Why it's about square root of x? What is the reason really? Of course, all the asymptotic considerations, function theoretic ideas that we had doesn't give much insight into that. Now, the evidence comes from analog problems. So I have chosen a toy analog problem here. Analogs of prime numbers. Of course, you can look at irreducible polynomials. I think that's a very good analog, because irreducible polynomials are the ones that you cannot write down as a product of two non-trivial polynomials that have smaller degree than the original polynomial. That's like the prime numbers, okay? And it turns out that there is a prime number theorem for polynomials. And that also comes from the work of Gauss. So let Am be the number of monic irreducible, monic for convenience, okay, of counting them, monic irreducible polynomials of degree n in the polynomial ring Fx, where let's take F to be a finite field with Q elements. So Q has to be a prime power, okay? Of course, Gauss looked at such things. I mean, there is structure here coming from algebra, of course, from the polynomial ring. And Gauss was very interested in such objects. And his book on arithmetica, his famous book, of course, influential book, is full of results like this, okay? He just settled the foundations. Then you can give a formula for this, okay? And then it turns out that here is an asymptotic. An is equal to q to the n over n plus an O term, q to the n over 2 over n. You see the power is a lot smaller. So this is an error term. Now, how do we get this? Of course, I will again surf now over results. We know from the work of Gauss that Gauss gives a formula for An. It's a cute formula. It's 1 over n times, and we are used to seeing such sums, divisors over n over divisors over n, a sum, mu d, and we are also used to seeing mu, and it makes an appearance, q to the n over d. That's the exact formula. Gauss gets an exact formula in this case, where there is structure. But now if you pay attention to this, d is equal to 1 seems to be the heaviest term. Mu1 is 1, so you get q to the n over n. Then you look at d is equal to 2. Of course, if n is even, you consider that term. That comes with a minus, q to the n over 2 over n. And then plus minus some terms. I mean, where, of course, terms like this, q to the m over, let me see, n. So I divide everything by n, of course. So other terms are like this, q to the m over n, where m is at most n over 3. I mean, I look at these, which are greater than or equal to 3. Now, what is the number of such terms? Well, you can see easily, the number of such terms is less than or equal to 2 to the number of distinct prime divisors of n. But that's definitely, since each of these primes is greater than or equal to 2, that's just less than or equal to this product. But then that's less than or equal to just n, right? So because these are just distinct prime divisors of n, so I can assume. So then the number of such terms here is definitely at most n. but each of them has an n below. So when I estimate, I only get these n's just cancel. So the contribution of smaller terms just give us at most n times q to the n over 3 over n. So they just contribute at most like q to the n over 3. But you can bury that into the secondary term here because n over 3 is a lot smaller than n over 2 in the long run. Okay, so you can definitely say that that's O of q to the n over 2 over n. I mean, so, but this term is also like that. So there you go. So that's the main term and that's the error term. So the prime number theorem for polynomials like that is proved. Okay, but now let's look at it with in the following way. Let's call capital X as q to the n. I think the important quantity here in this formula is q to the n. You have to rewrite everything according to that to see what's going on. If x is q to the n, then n is, well, this is the first time I need a logarithm to the base q, okay, log q of capital X. So I can represent n like this, and I can easily represent my formula in this way. So it's capital X over log to the base q of x plus, now look at the error term. I have to take the square root of this, x to the square root over, well, a logarithmic term. Now you can see that the error term is at the quality of square root. So there is the main term, and we are used to seeing x over log x as the main contribution. So in some sense, this is really justifying this analog problem, is really justifying this. It's even a little bit better, I should say, because of the structure that's present. But really, those are the big evidences about the truth, maybe the truth of the Riemann hypothesis, since these analog problems are well behaved. So people believe the Riemann hypothesis. And of course, there are elaborations on this. I mean, like Wales conjectures. I mean, these were just an amazing theorems from the last century and were proved settled in the 70s. So Wales conjectures. So they indicate they form evidences about the truth of the Riemann hypothesis. But nevertheless, it's still an open problem to show things like this. And I don't know if this is the best way to approach the Riemann hypothesis, but it's nevertheless an equivalent form. And people are producing different equivalent forms of the Riemann hypothesis, I should say. I mean, there are probably thousands of equivalent forms. I should close with an observation. Now, I think you can clearly see that observation. Just my closing point about this formula, which we cooked up easily from the prime number theorem with an error term, classical error term. Now, if you look at this carefully, definitely this secondary contribution is positive because this is a lot smaller than this. Doesn't matter if this is a negative error, this is bigger, but this is positive contribution. So one immediately sees that, I mean, in the long run, pi x is always bigger than x over log x, something that we can't see from the earlier statements. So, and in fact, that's in agreement, as you can see, because we had the graph. And that was our observation. And I mean, it continues to be like that. I mean, this behavior never changes. Pi x is always bigger than x over log x in the long run. And you can make a numerical study of how precise that is. And there are papers like that in the literature, okay, comparing pi x with x over log x, recent papers. And I think with our prime counts, and in this table, I think that's the only case where x over log x is bigger than pi x. After that, it's always less. So then one can make a conjecture here. Maybe it's also like that. That needs a numerical study, but at least in the long run, you can immediately prove that pi x is bigger than x over log x. So I think there is substance in all of these things. What I did here is doesn't have any arithmetical content, okay? This is just taking the viewpoint of function theory. So what we did here is, in some sense, function theoretic. All the contributions are like that. Maybe the subject is expecting a new revolution. Maybe we are expecting some advances on the arithmetic side. I mean, that's my opinion. We have consumed maybe the function theoretic side up to this point. Maybe new ideas are needed on the arithmetic side, I should say. But I think this was a useful, hopefully useful overlook of the prime counting functions. So I would like to stop at this point. If you have questions.
Hey, thanks, Professor Alkan, for your excellent talk. And if any question, please ask your questions.
Are there any questions?
Yes, I think.
I have a question, if I can ask.
Yes.
Okay, so you said Riemann was the first person to consider the zeta function as a function of complex variable. Is this really true? Because I heard that Eisenstein and Jacobi also studied the zeta functions for complex values. And I also heard that Eisenstein really had a proof for the functional equation for the zeta function that Riemann found.
In fact, before Eisenstein, I mentioned that Euler had the zeta function. But
yes, but as a complex function, as a function S inside the complex number, studied only for real values.
Yeah, that could be the case, but
and also it is interesting that Euler studied for negative values for S, the zeta for the values of the zeta function for negative.
Yeah, that's exactly the reason behind analytic continuation. And in fact, that was also Riemann's the very first motivation, which is not in the paper, but he wants to understand why Euler is considering the zeta function at negative integers. So that's what Riemann was trying to understand. And with that motivation, he considered the zeta function. I think Riemann's main contribution was to apply it really to the case of prime counting function. That was his main contribution, I should say.
And also in that paper of Riemann, there is an explicit formula that finds the Chebyshev psi function in terms of the zeta function as an equality, not as an asymptotic relation.
Yeah.
And do we have such a equality for pi of x? Do we have an equation?
We have. In fact, Riemann's paper has that. Yeah, we have. But it looks awkward. So that's why I didn't put it. So we have a formula. It contains analytic continuations of Lie of x at terms like x to the rho, where rho ranges over the critical zeros. But Lie at x to the rho needs a definition. I mean, because x to the rho is a complex number now. So how do you define Lie of x and things like that? You have to really make a preparation there, which I didn't want to do. And Riemann omitted those terms because they were awkward to calculate. So he thought that maybe they are not influencing the main terms that much. So he only took the main terms in his approximation, and that's what I presented here. But he has an exact formula. But unfortunately, we cannot control the errors there in that formula. That's the main problem. We cannot estimate them, okay? We can estimate, but we get useless output when we estimate. So in fact, they are in some sense oscillating terms. And maybe there are some cancellations among those terms, but we cannot detect those cancellations. And Littlewood's result was also presenting in that direction. So that the smaller order terms are also influencing the situation in the long run, because pi x minus li of x changes sign. So they are then as significant as the main terms or even the secondary term. So I should say. So.
Thank you. And also about the Riemann hypothesis, he calculated the zeros of the zeta function, I don't know, maybe 2 or 3 of them by hand during his time. I wonder, can you explain a little bit on the method that he used to find these zeros of the zeta function on the real line s equals 1/2?
Yeah, there is, he uses an approximate, he uses a formula. There is a formula for 1 over rows. So 1 over the critical zeros. So rho is a critical zero. So there is an exact formula for 1 over rows. And just elaborating on that formula, you can calculate somehow that there are no critical zeros whose imaginary parts are, I guess, less than 7 or something. And he elaborated on that. And I think the first zero appears around 14.1 or something. I mean, he had a calculation of that. And in fact, it's understood that he had a representation of the zeta function. And using optimization techniques like saddle point method, he had a way of calculating the roots, so which he didn't publish these results. So that's called the Riemann-Seagull formula. So he has a formula for the zeta function, which I cannot replicate here because I don't remember. And it was in his writings, and they were forgotten for a long time. And they were published by Seagull in 1935. Like 70 years after Riemann died. And it was a major contribution to the field at that time. So through that formula, you can effectively calculate zeros on the critical line up to good precision. And this formula is still being used today. I think like into the millions, the zeros are located on the critical line. And there are tables also about them, which I didn't, of course, reasonably go into them here, but there is also a lot of numerical data, I should say, on the critical zeros as well. I mean, that should take like another talk. And overall, it's not reasonable to just spend one talk on this. I mean, it could take an entire semester maybe to describe what Riemann-Seagull formula is. But it seems that he had more insight than we could expect, okay? Because this short paper is just a resume of what he was doing, we should say. I mean, he had a lot of more, and maybe even more, and all of these were unpublished. Riemann was a guy who didn't have the time to publish. I mean, he didn't polish his results. He was full of new ideas, but unfortunately his ill health also didn't give him the opportunity to make polished representations, publications of his results. So he was really unlucky in that case. But he had great insight. I mean, he didn't complete many of the arguments, but his insight turns out to be the correct one, and it's still motivating us nowadays. And that's why I guess one of the millennium problems is devoted to this. Although it looks like a unstructured problem, as time goes by, I mean, one can see more and more structures here. And analog problems are also playing a role in this. And I think that's the best I can say at this point.
Thank you very much.
Mhm.
Okay, is there any question? There is a question in the chat. He asked that for computing zeta zeros, one make lookup chapter 15 of.
Yeah, there are standard texts, Titmarsh's book or
and
Edwards' book. Edwards' book has a lot of historical side, which I am also using Edwards' book. So it's really a good read. I mean, you should look at that definitely if you are interested. It contains lots of the calculations as well on the calculation side. I mean, anybody numerically interested in the zeros also should take a look at Edwards' book. Titmarsh's book is more on the theoretical side. I mean, it's heavier, but it's still a very good treatment of the subject, I should say.
Simi has asked that title of the book. Oh, yes. Yes, Professor.
I think that it's the Riemann Zeta function. That's the title. Edwards' book has that title.
Okay. Thank you.
And this remark is also important. Matiasevich is doing some computational work. I have seen that as well. I think that's also good to remark. He's also doing work on truncations of the zeta function, like looking at partial Dirichlet series and doing some numerical work on that. So there are also interesting things that are going on nowadays there.
It's great. Is there any question? Okay.
I thank all of you for attending my talk.
Thank you again, and many thanks, Professor Alkan, for his great talk. And many thanks all for your participation. I hope to see you again at the next week, where probably, I think so, our last session will be held in the first season. Anyway, we will inform you through our Google group. Thanks again, and I should stop the recording and finish the session.